water management system in the Delaware was based on human need. How much water did New York City need? How much water did the down basin states need? Without any regard for ecological flows, how much the river needed.
As we go through cycles of droughts and floods, it becomes difficult for people to see in many cases that what's available on average is not something that you can count on.
One of the things that is so valuable with the flexible flow management plan that was based on the Columbia University work and the operational analysis is the fact that you can have it all. You can have a system that provides water supply for humans as well as the ecological flows that are necessary for the river.
A coalition of environmental groups started focusing its operations research on solving that problem to define some of the species and community needs in the river.
What I think is very important is that the work of this group be recognized for the precedent it sets and the problem it solved, a real-world problem involving water supply, environmental interests, folks concerned about flooding, involved 4 different states and the city of New York, that could set an example for others in this field to come up with innovative solutions.
Good morning, ladies and gentlemen. I'm Robert Tudor, the Deputy Executive Director of the Delaware River Basin Commission. It's a pleasure to be here today, and I want to express how honored we are at the Delaware River Basin Commission at being selected as a finalist in this year's Edelman Award competition. The Delaware River Basin Commission is an intergovernmental body of the governors of New York, New Jersey, Pennsylvania, and Delaware, who together with a federal government representative manage the waters of the Delaware River from a regional and systems perspective. Established in 1961, the DRBC's responsibilities include water supply allocation, drought management, and flood protection. As such, the DRBC is the implementing agency for the Delaware River's new Flexible Flow Management Program, an innovative and highly beneficial approach to management of water releases into the Delaware from 3 important reservoirs on its headwaters. A Conservation Coalition research team comprised of Jim Serio of the Delaware River Foundation, Colin Apps of the Nature Conservancy, Nat Gillespie of Trout Unlimited, and Dr. Peter Colasar of Columbia University carried out the operations research that was instrumental in the establishment of the FFMP. This morning we'll be telling you about the Flexible Flow Management Program, the operations research that led to it, and the benefits it brought to the citizens of the region. But first, a few words about the river. The Delaware has its origins in the Catskill Mountains in New York State. Small forested streams feed into the upper reaches of the west branches of the Delaware and come together at Hancock, New York to form the river's main stem. The Delaware then flows some 330 unimpeded miles past Pennsylvania and New Jersey into Delaware Bay. At its southern terminus, the Delaware is the largest freshwater port in the world. DRBC is one of a few river management agencies in the United States that manages from the mountains to the sea. For the purposes of today's presentation, however, I want to focus on the upper reaches of the Delaware system. The upper reaches are one of the finest wild trout fisheries in the United States, and the 3 reaches of the non-tidal Delaware River are included within the United States National Park Service as part of the Wild and Scenic River System. The Delaware supplies water to some 15 million people, 8 million of them in New York City. Since the Delaware passes through 4 states and serves major American cities, water resource issues can be contentious. In the 1920s, New York City, itself not in the Delaware Basin, proposed to dam its headwaters and divert water from the Delaware for its own use. New Jersey brought suit to block the city, and the issue was resolved by 2 U.S. Supreme Court decisions, which gave the city the right to build 3 dams and divert up to 800 million gallons of water per day. subject to the constraint that it maintains a minimum water flow of 1,750 cubic feet per second, some 100 miles downstream at Montague, New Jersey. That would be the intersection of 3 states, New York, Pennsylvania, and New Jersey. These 2 parameters, the 800 million gallons a day New York City entitlement and the 750 cubic feet per second at Montague flow constraint, will figure heavily in the operations research analysis you will be hearing about this morning. The Supreme Court also required that changes to the Delaware water allocations be unanimous among the parties to the decree, that is, the 4 states and the City of New York. This requirement for unanimity will also figure importantly in today's story. I can tell you a win-win solution was absolutely necessary. What brings us here this morning is the successful application of the operations research to resolve 2 issues that were not under adequate consideration at the time of the Supreme Court cases. First, since the 1970s, there have been running, often acrimonious, disputes between the fishing community and the managers of New York City dams over the quantity of the water releases. The dam managers, whose mission is supplying water to the city, advocated policies that hold the water behind the dams, employing a rationale that, and I quote, the drought of the century may be starting tomorrow. But fishing and environmental communities argued that the environment had been persistently shortchanged of the cold water it needed. Second, the Delaware Valley suffered 3 record-breaking floods between 2004 and 2006, and Valley residents wanted the dams to provide increased flood protection. The coalition research team, using operation research, balanced the 3 issues of assuring water supply, increasing river habitat, and providing flood mitigation. Their work led to the DRBC's successful implementation of the FFMP in October of 2007. Now, they will tell you the analytic and political story behind the success, but before they do, I should like to clarify the relationship between DRBC and the coalition. This was not sponsored research. Neither the DRBC nor any of its members were clients of the coalition. The coalition itself was an informal, ad hoc group of volunteers who saw a need and brought their dedication, insights, and operations research methodology to us. We in the DRBC and the citizens of our 4 member states have been the beneficiaries of this truly pro bono effort. I'm amazed at how much they achieved with such modest resources, and I and the DRBC thanks them. It is now my pleasure to yield the podium to Jim Serio. He's a member of the coalition, founder of the Delaware River Foundation, a longtime advocate of sensible water management, and importantly, a man who has for many years lived on and been a trout fishing guide in the upper Delaware. Jim will describe for you the water allocation problems from the viewpoint of the fishing and environmental community. Jim?
Thank you, Bob. Hello, I'm happy to be here representing the environment and the critters that live in the Delaware River. I'd like to explain the river water release issue from an environmental perspective. At the outset, I want to emphasize that if our coalition had had a client, which we really didn't, the client would have been nature. We coalition members are all fishermen, yet we were not working to make trout fishing better or increase fishing revenues in the upper Delaware, although the FFMP does accomplish both. Our focus was on the environment of this beautiful river, and our research was driven more by an aesthetic and moral imperative than by economics. We will be talking a good deal this morning about trout and trout habitat, largely because they are the canary in the Delaware River coal mine. If trout are healthy, the river is healthy. So when we speak about trout or trout habitat today, please see this great wild natural river and think lots of cold, clean water. The heart of the dispute between fishermen and city reservoir managers was that summer cold water releases from the dams had been unnecessarily low and variable, thus limiting the size and viability of the trout population. Year after year, most recently in 2003, 2004, and 2005, summertime releases dropped to perilously low rates, even while there was plenty of water in storage. What was wrong? First, the base rate of summertime releases was too low. Second, river managers depended on an unworkable bookkeeping mechanism that set water aside to alleviate thermal stress on fish. But those thermal relief banks were too small, and their administration was much too cumbersome and arbitrary. Third, the release rules, quite remarkably from an operations research viewpoint, did not take into account the most important characteristic of the system, the amount of water in storage. New York City believed that it was too risky to release more water in the summer. In a nutshell, the mission of our coalition was to show them how it could be done at no increase in risk. That is what the Flexible Flow Management Program is about. Releases from Cannonsville Reservoir are particularly important to trout habitat. Let's talk some numbers here. While a Cannonsville release of 300 cubic feet per second is needed just to wet the river from bank to bank, on many days, actual releases were as low as 45 cubic feet per second, a level that is truly devastating. These two photos show the dramatic change in the river when releases drop to such low levels. Were these releases justified from a water availability perspective? Not at all. Let's take as an example the environmental crisis that precipitated the unification of the Conservation Coalition. On July 10, 2005, the reservoir stood at 88% capacity, a level of protection well above DRBC's drought watch of 63% capacity. Air temperatures in the upper Delaware Valley were in the upper 90s. The release on that day was a paltry 125 cubic feet per second. River water temperatures soared into the lethal range for trout, and stream beds were exposed, leading to the destruction of aquatic insect populations on which the trout depend. In fact, one bad flow day can result in destruction that takes years to recover. A public meeting was called by the DRBC after it had rejected a petition from the fishing community to institute temporary emergency release program. The DRBC's analysis supporting the rejection was unconvincing, and it looked to us that a more thorough operations research-based examination was needed. Moreover, two statements made by the commissioners at that meeting provoked the authors to action. The first was a candid admission by a commissioner that we always knew these design flows would only be adequate for 50% of the time. So why do you fishermen come back here complaining every other year? The second was that as long as the fishing community speaks with multiple voices, you will not be taken very seriously. At this time, I would like to introduce Dr. Peter Colasar. Peter is an Edelman laureate and Professor Emeritus of Operations Research at Columbia University. It was Peter's methodical operations research approach to the Delaware flows that led to the development of the Flexible Flow Management Program. Peter?
Thank you, Jim. Good morning, everyone. It's a real pleasure to be back here in Edelman land. This morning, my mission is going to be to explain the Flexible Flow Management Program to you and the operations research that lay behind it. Let me just make a little comment before I get into that we'll all be listening for the role of operations research in policy formulation and optimization, but it played a very big role in just bringing us together, in bringing together the differences within the coalition and in bridging the gap between us and to the politicians and administrators who ran the system. So having said that, let's really get into looking at the system. We've got a schematic here which is going to show you the essence of the Upper Delaware system. The schematic shows you the three main dams of New York City, Cannonsville, Pepacton, and Neversink, and as they're positioned on the Delaware's East Branch, West Branch, and Neversink River. Now you can see the diversion tunnels to New York City and the important USGS gauge that gauge that plays a role in the Supreme Court's decision down at Montague, New Jersey. The diagram does show the different reservoir capacities, but it can't capture other crucial differences. Differences in speed of refill of the reservoirs, differences in the drinking water quality, differences in their ability to contribute to the trout habitat. Now, this map is going to show you the trout habitat in the upper Delaware as it was at the start of our work. The blue coding is good, red is bad, and one of our goals was to get as much blue as possible into the system. And as Jim said, think here, cold, clear water. Now let's take a quick look at how the old release policy worked. These decisions are made every day. So each day the Delaware River Master would estimate the releases needed to meet the Supreme Court's dictate of 1,750 cubic feet per second at Montague. Then New York State would take those numbers and augment them in order to meet their conservation flow targets. And then in situations in which the temperatures were high in the river, they might augment those releases with additional water from the thermal bank that Jim mentioned. That is, if there was water left in the bank account. Finally, these aggregate releases were passed on to the New York City dam managers who would allocate the releases across the dams. So now let's look at what we changed in FFMP. Basically, we increased the conservation releases. And, importantly, we keyed them to the amount of water actually in the reservoir, actually in storage. And in an important simplification and controversial simplification, we eliminated the thermal banks. Now, what we did from an OR viewpoint is we keyed release quantities to storage levels through a feedback mechanism that we called adaptive release. And we represent adaptive release simply as a matrix of release quantities. There's a column for each reservoir. There's a row for each storage level. And the entries are the minimum releases for that day if the reservoir storage is in the indicated range. Now, in the example we've got on the screen before you, the high storage range runs, as you can see, from 75 to 100% reservoir capacity, and the matrix specifies that the release per Pacton reservoir would be 500 cubic feet per second. By contrast, in the lower level, Drought, the release from Neversink is only 60 cubic feet per second. So that's the essence of adaptive release. But a release policy would have to be a set of such matrices. In principle, there could be a release matrix for every day of the year, and different matrices are required because of the seasonality of precipitation and water usage. So, to design an adaptive release matrix, you have to choose the release quantities, the number of release levels, the release ranges for those levels, and you have to specify the number of planning seasons, that is the number of release matrices, and there could be, say, as few as 2 or as many as 365. So our goal, our mission, was to determine these parameters, that is, find a policy that would increase trout habitat, but balance this with considerations of water supply risk and flood protection, and this really is where the operations research comes in. So, here is FFMP's actual implementation. It has 7 release levels, and there are 9 seasonal matrices. And one of the most critical and politically sensitive decisions that we had to make was a specification of the release level ranges. And as you can see in this example, there's a so-called normal release level, and that occurs when reservoir storage is between 60 and 90% capacity. Why 60 and 90% capacity? Where those numbers come from? How did we choose them? Well, we picked the release levels to correspond to the traditional New York City drought curves. And here they are. These drought curves, and you can see they're seasonal curves, had been in place since the late 1970s. They're the city's definition of safe versus risky storage. So when storage falls below the curves, the system is technically in drought, and releases and diversions are curtailed. Now, our analysis had showed that these drought curves were flawed, but we made the political judgment that we couldn't change too many elements of the system at any one time, so we decided to include them in our FFMP design. So, in a nutshell, that's what FFMP is. Now let's talk about the OR that led to its development. So we started out with some basic systems analysis on the statistics of the reservoir operations. And here's some of the important things that we found. First of all, New York City takes 54% of the water out of that upper river. That's an enormous burden on the river. The total reservoir capacity was only 1 year of New York City's storage. In comparison to other systems, this is a very low capacity system. And shockingly, 25% of the water had been spilled over the tops of the dams. And in our judgment, spilled water is wasted water. And we saw early on that our principal leverage for increasing habitat without impacting water supply would be to convert wasteful spills to environmentally beneficial releases. And that was the game that we need to play. Also, reducing spills had a flood mitigation benefit. Now, while historical water supply was adequate on average, and we appreciate this as OR guys, variability was a serious problem. Supply and demand were very much out of sync. Large amounts of water come into the reservoirs in the springtime, and both New York City usage and these Montague flow target will peak during the summer. Then there are substantial variations in supply from year to year. And whenever the annual supply falls below about 750 million gallons a day, on average, you've got a potential for really severe water shortage. In addition, this is not a stationary system. Weather cycles matter. So in the 1960s, the drought of the century, what we saw was one low year, followed by another low year, followed by another low year. In short, we had 5 low years in a row. The reservoirs couldn't refill. There was a serious risk of literally running out of water. The DRBC was emphatic. They sought sustainability. Any viable release plan would have to handle the drought of the century. We'll talk more about that later. Now some more about our modeling. You know, we were unfunded outsiders, so we had to get started by improvisation. And what we did with some students at Columbia is created our own homegrown Columbia University simulation model, quite simple model. It reflects the schematic that you saw earlier, driven by some publicly available information on reservoir flows and usages. And we had it in an embedded quadratic program that allocated diversions and releases across the reservoirs. The purpose of that optimization was to maximize the drinking quality of the water that went to the city, but keep the reservoirs in a safe refill balance. This simulation, simple as it was, corroborated our theory that releases needed to be keyed to storage, and it also taught us, to our surprise, that it was wet summers in which the upper river would really get starved of releases. Worse, in wet summers, the large inflows to the reservoirs, coupled with the low Montague releases, would leave the reservoirs too full in the September hurricane season. So a major benefit of our FFMP program was to solve both of those wet summer problems. The management of dams, as you will appreciate, is a classical inventory problem. There's a substantial OR literature. But our system as a whole, with its physical and political complexity, would not admit of a direct application of that theory. However, OR tidbits really were helpful. The OR literature showed us that to minimize spilling, which was important to us, reservoirs need to be kept in refill balance. And our own joint work at Columbia with Professor Federgrun has proven that in order to balance water shortage risk, flood benefit, and also environmental benefits, we needed to have was a convex increasing function of the water storage. The releases, convex function of the storage. Both of these principles were embedded in the FFMP. So now, after a lot of work, in February 2006, the DRBC issued 2 edicts that would shape a lot of our research. First, they said a release policy would have to be neutral, drought neutral, as compared to their benchmark, and the benchmark measure was drought days. A drought day is a day on which reservoir storage falls below the New York City drought curves that you've just seen. Second, they made a dictate that only analyses done with their own proprietary Oasis simulation model of the Delaware would be entertained. And Oasis has got a lot of detail in it, and it's driven by a 73-year water history. So we went out and got a site license for Oasis and started the really hard task of getting an implementable policy that would balance the water supply risk with our goal of increasing habitat. So let me pose a question to you in sort of professorial mode. If you were to release an additional cubic foot of water from, say, the Papacton Reservoir in the spring, how many additional drought days would you suffer? And how many additional elements of trout habitat would you gain? Well, we had to answer a lot of those questions to do our design. So what we did to quantify these relationships was we carried out an orthogonal balanced array of simulation trials, quite an extensive series, the results of which we used to calibrate a set of regression models with very high reliability, high R-squares, in the 90s actually. And these regressions for both drought days and trout habitat as function of releases were incorporated in an Excel-based adaptive release policy analyzer and enabled us to really key in on our design without having to have recourse to extensive simulations as we went. Now, let me talk about habitat. Improving a trout habitat was our key goal. But at the beginning of the project, there was no metric for it. So while Oasis produced river flows at locations that were critical to the trout, no one knew what the real impact on the trout was until in late 2006, the U.S. Geological Survey produced a Delaware River habitat estimation model. And this model estimates habitat as an area, literally in hectares. It's an area of the river in which the depth, temperature, and stream flow is suitable for the fish. The model's inputs or outputs from the Oasis model, and it would produce these estimates by fish species, by section of the river, and by season. Needless to say, these estimates became central in our design. Now, our chain of research that I've been talking about culminated in midsummer 2006 when we developed something we called the Moderate Adaptive Release Policy. It's on the screen now. Very simple policy. We only had 2 seasons. We only had 4 release levels. So far from a finished product, this Moderate Adaptive Release Policy, however, its performance was attractive enough for us to take it on the road, to brief it to DRBC members and to other river stakeholders. And here's how it performed in a nutshell. Relative to DRBC's benchmark policy, this policy increased conservation releases by 95%, which added enormously to trout habitat. It decreased September storage in wet years by about 12%, thus providing some hurricane flood protection, and it decreased spills by 23%. Remember, we're needing not to waste so much water. And our detailed analysis, some of which you'll see in a moment, showed that there was no real increase in water supply risk for New York City. In addition, this is a really attractive policy from the fish's viewpoint in that detailed statistics really look good. The patterns of river flows captured in this graph on the screen before you really eliminated the worst of the low flow situations that the river has suffered in the past. But the killer question remained on the table. How would adaptive release handle the drought of the 1960s? And this time series plot is the beginning of the answer. This is a plot of reservoir storage, 1961 and 1968, and this blue curve is the storage under the DRBC's benchmark policy. Notice the severe drop in 1965 and 1966, which is the heart of this drought. Now, the red curve is a similar plot from our moderate adaptive release policy. The two curves largely overlap. So when the going got tough, during the worst drought ever experienced, our moderate policy performed quite as well as the DRBC benchmark. To make this point hit home, I asked, rather dramatically, during a public briefing before DRBC members and several hundred river stakeholders, can you see a difference? And during the coffee break, several DRBC members caucused, concluding, I think we've got to really listen to these guys. They've got something new here that might be of value. And from this point on, the relationships between us and the DRBC members changed from contention, confrontation, to one of collaboration, although without ever really being in total agreement. But how attitudes had changed. Only a couple of weeks earlier, at an important briefing at DRBC headquarters, the head hydrologist for one of the DRBC members had said, at the end of the briefing, said, Professor, you've got some interesting ideas here, but they're kind of out of the box. And my job is to stay in the box. Whew. By January 2007, however, after all this work, the DRBC had informally adopted our adaptive release proposal and framework as a basis for building a new policy. In the following months, we worked largely in collaboration with several of them, looking at habitat versus drought day trade-offs to identify feasible and efficient policies. And so we come to, in March 2007, we in the DRBC were in complete agreement on the policy structure and on 184 out of 189 policy parameters, essentially those release levels. The remaining difference between we and the coalition was that we suggested somewhat higher releases from Cannonsville would really be necessary to really give the trout benefit they were looking for. But we did not convince in those arguments, and they went and implemented the policy with the release numbers as you see here in October of 2007. But during the first 2 years of implementation, the policy performed essentially as we had predicted, and it showed the DRBC that the system could safely be improved by moving to the higher release quantities that we had suggested originally. So by June 2009, the DRBC modified the policy to come into almost exact conformance with our original proposal. I think in a way you could say that by now the adaptive release policy and the FFMP framework had become the new box. And now it's my pleasure to turn the podium back to Jim, who's going to discuss the FFMP's impacts.
Thank you, Peter. Hello again. In a few moments, Paul Rush, Deputy Commissioner for Water Supply for New York City, and Carol Collier, Executive Director of the Delaware River Basin Commission, will be joining us by video to speak about the impact of FFMP. But before we do that, I'd like to give you a bottoms-up assessment of FFMP implementation on the ground, that is, in the water. A little preamble is in order. In operations research, we often consider the ratio of benefits to project costs. We should tell you that the entire development just described was done at zero cost to the DRBC. Our entire budget for the project from its inception was less than $25,000. Now, I'll address three impact categories: water supply, fisheries improvement, and flood mitigation. First is water supply. This is arguably the most critical issue, and fortunately the easiest to address. Our goal was to improve the river environment, but to do no harm to New York City and other Delaware water users. This is exactly what FFMP has accomplished. As Commissioner Paul Rush will shortly testify, the Delaware's contribution to New York City's water supply is as secure as ever. Sustainability, sustainability, sustainability. This was the mantra we heard echoed by Decree Party members throughout the process. We believe that this has been accomplished. The second category is the environment and the trout. The word from fishermen up and down the Delaware is that not in recent memory have so many big, beautiful trout been caught or so many healthy juvenile fish been seen. Remember, trout are our canary for river health. The fish population and fishing are improving, and FFMP can be given at least some of the credit. But as nice as this on-the-water experience is, we designed FFMP to achieve long-run habitat improvements. The single most important metric is that, over the long run, adult trout summer habitat will increase by over 200%. Though it was not our original focus, we should share with you some fishing economics. Consider that FFMP improves existing habitat, extends the fishing season, and converts more river sections to trout habitat. Taking all of this into account, using data from the habitat model, we estimate a net economic benefit to the upper Delaware region from improved fishing of approximately $164 million annually. Our third category is flooding. There have been no serious floods in the upper Delaware since FFMP has been implemented. As Carol Collier and Paul Rush will testify, FFMP's induced reservoir voids have been reduced through 2009 and the spring of 2010. There was enormous precipitation this spring along the entire east coast of the United States, and flooding was widespread. But there has been no flooding in the Delaware Valley. In my judgment, without FFMP, there may well have been flooding in some areas of the river. Again, FFMP was not designed to prevent flooding in any given year, but over the long haul, its spill mitigation releases, by reducing reservoir levels at critical times, should moderate the risk. Although we tried hard, we were unable to estimate dollar benefits. Two elements were missing. First, the relationship between releases and flood damage is unknown. Recently, the Army Corps of Engineers has developed a model that can estimate how flood levels change as a function of reservoir operations. Second, no one knows the economic damage from the three great floods of 2004, 5, and 6. FEMA insurance payments for individual property damages totaled $226 million. This is just the tip of the iceberg, as many individuals and businesses were uninsured, and there was massive public infrastructure damage. In summary, everyone needed to win. That was imperative from the beginning of the project, and FFMP does just that. And the greater transparency that FFMP brings to the decision process has led to a better understanding of everyone's needs and has helped FFMP become truly flexible. And the best is yet to come. The FFMP framework and implementation are indeed flexible. And as Carol Collier will tell you, the DRBC is committed to continual improvement. The coalition team, using operations research, has been developing the next innovation, the augmented FFMP. And now let's listen to Paul and Carol give us their final thoughts.
If you look at the flexible flow management plan, it has served to change the management of the river. It is better. Fisheries have improved. There have been spill reductions, which helps the flood mitigation. So it has worked.
From what we hear from people who are using the river, we're seeing great progress. And from New York City, we're seeing no appreciable risk.
The analysis was, we were able to clearly see what the benefits were, and through that, each one of the parties was able to understand clearly what the risks were and what the benefits were to doing a complete change in the way the reservoirs are operated and releases are made.
The team came at the right time and with the right attitude so that the decree parties could move forward. You see situations like down in Atlanta, Georgia now with the water wars between Georgia and Alabama and Florida. And, that's sort of where we were heading.
What I think is very important is that the work of this group be recognized for the precedent it sets and the problem it solved, a real-world problem involving water supply, environmental interests, folks concerned about flooding, involve 4 different states and the city of New York, that it could set an example for others in this field to come up with innovative solutions.
The river is always changing, and we'll never have just one plan in place. So Peter Colazar and the Columbia team don't have to worry about the future because we'll be calling on them again as we go to the next stages.